Hi, I'm Prof. Al. Welcome to Chemistry Matters. And today we're going to be taking a further look at hybrid orbitals. And specifically, we're going to look and see how we can describe multiple bonds in organic compounds using the concept of hybrid orbitals. Okay, so for those of you who watched the previous video on hybrid orbitals, you'll remember that in that we were looking at how to describe the bonding in methane, CH4, a tetrahedral molecule, 4 bonds, or 4 CH bonds around the carbon, and we found that we could do that if we took the valence orbitals of a carbon atom, the s and the 3 2p orbitals, and we hybridized those. We mixed them up essentially and divided by 4, and we ended up with 4 sp³ hybrid orbitals. And we said, okay, this is good. We can describe essentially the geometry of any carbon-containing molecule, provided that we don't have any multiple bonds in there. Multiple bonds introduce a complication, but we can still explain what's going on with hybrid orbitals. So let's get underway and do that. So let's have a look, for example, at this molecule here. This is the simplest possible multiply bonded carbon-containing molecule. That is ethene. C2H4. What do we know about ethene? What experimental features are we trying to reproduce in our explanation of this structure? First of all, it's a planar molecule. So all of those atoms lie in the same plane. Second of all, bond angles, 120 degrees. Okay, so all of these CH bond angles around the central carbons there, all 120 degrees. So those are the two factors that we need to reproduce if our hybrid orbital theory is worth anything. Okay, so let's see if it is. So let's kick off again, as we did with our sp³ hybrid orbitals, by looking at the valence electron configuration of carbon yet again. Okay, so here's your 2s and your 2p orbitals, like so. Now what are we going to do? We are going to hybridize these orbitals again, almost just the same as we did for the sp³ situation, but now we are only going to hybridize or mix these guys, this 2s orbital and 2 of the 3 2p orbitals. Okay, so when we do that, what do we get? Well, we're essentially going to add these 3 up now and divide by 3, and we're going to leave this one alone. So when we do the hybridization, now what we're going to get is something that looks a little bit like this. Okay, so we have got 3 now degenerate orbitals that we get from mixing the 2s and 2 of the 2p's, and we get this lone orbital out here. We're going to call this pz, just for argument's sake, and that remains unchanged from here. But now the big difference is we've got 3 hybridized orbitals, okay, which are made up of a single s orbital and 2 p orbitals, and so we're going to call these sp² hybrid orbitals. And we've got 1, 2, 3 of those. 3 sp² hybrid orbitals. So that's where the hybridization process gets us in this case. Okay? So, same as last time, what have we got? We've got 4 electrons that we need to put in these orbitals. So let's put the 4 electrons in. We're going to go 1, 2, 3, and we're going to be naughty and we're going to put that 4th electron into that orbital. Now normally, Hund's rule would say that you're not allowed to do that, but rules are made to be broken, and this does agree with experiment. So let's be a bit naughty, and instead of putting that 4th electron in here, we're going to put that 4th electron there. We'll see why that works in a minute. Okay, so what's that going to allow us to do? Well, it allows us now, we can form 3 bonds with this and another bond with that. Now, we've got 3 equivalent sp² hybrid orbitals. So in other words, we've got to put 3 things now around a central carbon atom. And what's the best way to get them as far apart as possible? What's the best geometry for that? Well, bond angles of 120 degrees, trigonal planar geometry. Okay? So that's going to give us a trigonal planar geometry around our central carbon, which is exactly what we want to reproduce the bonding in ethene. Okay? So to have a look at that in terms of a diagram, let's again go to the good old textbook and show you what's happening in picture form, okay? So we're taking one 2s orbital here and 2 2p orbitals now. We're plopping our s orbital into the middle of that essentially and dividing by 3, mixing them up, divide by 3, and now you end up with 3 sp² hybrid orbitals. And again, neglecting that little lobe, which just complicates things, we now arrange these at 120 degrees around the central carbon atom, like so, okay? So that's the sort of arrangement now that we're going to get around our central carbon atom. So let's now imagine taking 2 carbon atoms that are sp² hybridized, okay? So here's a carbon atom that's sp² hybridized. Here's a carbon atom that's sp² hybridized. Each of those sp² hybrid orbitals contains a single electron. So now this sp² hybrid orbital can overlap with a hydrogen orbital, a 1s orbital that's spherical and form a single bond. And it can do that there as well, and here as well, and here as well. So there's 4 CH bonds, which is all good. Here we're forming a carbon-carbon bond now through overlapping this sp² hybrid, which contains a single electron, and this sp² hybrid, which also contains a single electron. That's going to give us a carbon-carbon bond. So we're all set. We've got now our planar carbon framework. Okay, we've got 4 CH bonds and a single carbon-carbon bond. The only thing missing now is the double bond. Where does that double bond come from between the carbon and the carbon? Well, if you remember, we haven't used that pz orbital yet. Okay, and that pz orbital contains 1 electron. And that pz orbital is oriented with respect to the rest of the molecule at right angles. It's perpendicular to the rest of the molecule. Here is your carbon atom, hydrogen, 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 hydrogen. Let's now use the pz orbital on both of those carbon atoms now. So here is a pz orbital that contains 1 electron and it's pointing up and down. Here is the pz orbital on the neighboring carbon. It contains 1 electron and it's pointing up and down. So these guys can now overlap side on and they can form a pi type overlap between themselves, like that, a side-on interaction, above and below the internuclear plane. Here's your carbon-carbon bond, single bond. Here's the pi bond. And if these guys overlap, which they will do because this is in phase, that'll overlap with that, that'll overlap with that, and eventually you get this, let's call it a pi cloud, above and below the plane of the rest of the molecule. And what we've done there is created now a carbon-carbon double bond. Okay, so our double bond is made up of a sigma interaction and a pi type interaction. And the overall molecule, you could say, looks now like this, okay? Where we're viewing it from sort of side on. Here's your carbon-carbon single bond, that sort of orangey colored there. Your CH bonds, the orange-red overlaps. And here is your pi interaction here, the above and below situation, okay? And that now explains the overlap that you get in ethene. We've really replicated the experimental details of the ethene molecule. Remember, what we wanted was bond angles of 120 degrees, which we get because of the 120 degree orientation of the sp2 hybrid orbitals around each carbon atom. And also we wanted it planar. And we've got a planar molecule. All of those carbon and hydrogen atoms are in the same plane. And we get, remember, our double bond from utilizing the pz orbitals on both of those carbon atoms like so, above and below the plane of the rest of the molecule. Whoops, let's put that in the other way. And we get an interaction there, which is a bonding interaction, and that now makes a pi bond. So we have perfectly replicated what we know experimentally about the ethene molecule, again, simply by utilizing these hybrid orbitals. In this case, sp2 hybrid orbitals. Now, we could, but we haven't got time, do exactly the same thing for the ethyne molecule. And the ethyne molecule is the simplest triply bonded molecule. It looks like this, okay? And what we would find with the ethyne molecule is sp hybridization, where you're overlapping or you're taking a 2s orbital and a single 2p orbital. From that, you end up with two sp hybrid type orbitals and unused px and py type orbitals, and that gives you your triple bond. Your triple bond is made up of a single sigma overlap and one pi overlap there and another pi overlap there. Okay, so I'll leave that for you guys to do as an exercise. It'll be in the textbook or hopefully in your notes anyway. We won't go through it, as I say, in this case, but it's entirely analogous to the sp2 that we have just covered. Okay, so essentially with that, we've got sp3 hybrid or hybridization, and that explains singly bonded carbon-containing molecules. We've got sp2 type hybridization, that explains doubly bonded carbon-containing molecules, and sp type hybridization, that explains triply bonded carbon-containing molecules. So essentially we've explained pretty much all of organic chemistry geometries and multiple bonding types of molecules simply by using this idea, this concept of hybrid orbitals. Okay, so with that, I think you've probably learned a thing or three about organic chemistry today, which is all good, and we'll see you in the next video.